So good morning. Thanks for making it. I know it's early, 9 o'clock on a Sunday after a big party. I'm going to be talking today about building password dictionaries, actually passphrase dictionaries, and utilizing Amazon EC2 to crack passwords. All right, well, so it's 9 a.m., it's Sunday. My guess is many of you were up late. How many of you went to the party last night? All right, the rest, wow, almost everybody. So some of you are probably still drunk, have had some beer, and some of you probably are hungover, but I'm glad that you're here. So who am I? So my name is Steve Werby. I'm an independent security researcher and consultant. When I signed up to give this presentation, I was the Chief Information Security Officer at the University of Texas at San Antonio, and then I decided I didn't want to do that anymore, and so now I work independently. In terms of my background, I've been in the field since 1999. The last 6 years I've worked as a CISO. Before that I did hands-on technical work, and that's what I'm getting back into. Okay. Here's a list of my credentials. Here's the ones I still have. I'll let all the ones that are struck through lapse. I don't know if this is good or bad, but probably my 15 minutes of fame is I put this joke out on Twitter, and it got picked up a lot. So I think that's where I peaked about a year ago. Another thing that I'm known for is since 2009, I haven't signed my own name on anything the same way. So when I go buy something on a credit card, I like to make stuff up. So on the left-hand side, I put some JavaScript in as my signature. On the right-hand side, I actually signed something about DerbyCon. I've only actually been called out once for this, and it was prior to a presentation in April. My co-presenter and I both did this, and the waitress came and said, "Would the two of you like to re-sign this with your real signatures?" We both said no, and she was okay with that. I want to make this interactive. We have a pretty small group here today, so if you have any questions, feel free to jump in. If it looks like we're not going to have enough time, then I'll move us along and I'll be available to take questions afterwards. I'm probably going to ask you some questions as well. And every good presentation has to have a disclaimer, so I ask that you read this and agree to it.
Agree.
All right, so there's my real disclaimer. There's a few things I'm hoping that you'll take away from this presentation. Let me back up a little bit. How many of you have used Amazon EC2? Okay. How many of you used it for something information security related? Okay, so maybe a quarter of you have. So what I want to do is expose the rest of you to Amazon EC2 and give you an idea of what it could potentially do for you from an information security perspective. I'm going to talk to you about some tools that you can utilize to crack passwords. And we're going to discuss a little bit about whether it's better to build your own device to do that or to lease using something like Amazon EC2. And then we'll talk about the difference between passphrases and passwords and building passphrase dictionaries. And we'll talk about hashing algorithms a little bit as well. So I assume almost everybody knows about, well, probably everybody in the room knows what hashing is, so I'm not going to go into a lot of detail. There's a lot of hashing algorithms. Some are better than others. Some are extremely fast. Some are a little bit slower. Some have collisions and some don't. But they all essentially work by taking a string, parsing it, and outputting what should be ideally a unique string. There are a lot of bad implementations of hashing. Hashing should involve a salt, which makes it much more difficult to crack the password. We're going to see some examples of some leaked password data breach exposures from the past year, and all those did not use salts. So does anyone want to take a stab at what hashing algorithm is probably the best to use from a password storage perspective?
Decrypt or KDF.
Perfect. Those are the two that I'd be looking for. But pretty commonly we see MD5 and SHA-1 still being used, and they're very trivial to enumerate through to guess passwords. Okay, so we talked about those two. And the reason bcrypt is good is bcrypt, well, the two that were just mentioned are the only ones that I'm aware of that basically do not degrade in performance as Moore's law takes effect. So bcrypt, for example, can have a work factor applied to it so that it can be modulated to take longer for the hashing algorithm to be performed, which is a benefit when you want to deter against password cracking. So I'm not going to go into detail about all these. The leak that we're going to look at today is the eHarmony leak, which involved 1.5 million unsalted MD5s. The rest of these, except for RockU, that was from, I believe, 2009, were password leaks from the last year. Does anyone know what's different about the IEEE password leak?
Oh, that was in files.
They just left it out on a
Yeah.
TP, I think, for a month. Or
Right.
A server.
Well,
Wide open to everybody.
Correct. It's actually possible it may have been exposed for more than a year, but the interesting thing about that one is that it wasn't the password database that's believed to have been exposed. It was logging for the web server that was published to an OpenFTP site. For the rest of these, it's believed that it was the password database that was actually compromised. In terms of cracking, what we're going to be looking at today is offline cracking. You can also perform online cracking by doing vertical, horizontal, or diagonal attacks, which for a vertical attack, that's when you take one user ID and apply a lot of passwords to it. Horizontal is when you take one password, enumerate it across a lot of user IDs, and diagonal is when you do a combination of those. By doing that, it makes it easier to defeat controls that would look for password attacks. And pre-computation are things like rainbow tables, where essentially, to make it simplistic, you have a plain text password and the encrypted or hashed counterpart to it, and a simple lookup of a hash is done to find the plain text password. So that can be done very quickly, but a tremendous amount of storage is required if the length of the passwords and the key space is very large. So the password attacks we're going to look at today are dictionary, rule-based, and brute force attacks, and a variant of that called a masking attack. So why do you care? So it's really fun, perhaps, to go find a password database that's been leaked, take 1 million hashes and try to crack them. But can you think of any other reasons that might be valuable to you as an information security professional?
See what your users are using over and over again that you may need to limit.
So that's a good point. So looking at your own environment to see if your user's behavior is meeting your expectations. Another reason that I've done it in the past is to make a case for modifying password policies. So if I work with executives who believe that an 8-character password is strong, just because it has a requirement for a minimum of an uppercase, lowercase, numeric, and special character, by performing a password attack, I can show them how easy it is for an attacker to acquire the plain text passwords that the users are using. I also use it to make the case for things like two-factor authentication. Can any of you think of any edge cases where it may be valuable? So in your environment, if you have a user who leaves, what do you typically do to their passwords?
Disable them and zero it out.
Okay.
To a random that no one knows.
And so if it was an account that you needed to maintain access to, would you then change the password?
Then we just redo the rights. You know, so from a legal standpoint, we don't change the account. We leave the account alone and just grant rights to whatever they need.
Okay. So how many of you in your environment have people that utilize third-party services? And do you perform key escrow for all those third-party services? I find that most people don't, and since it's pretty common for a user to use the same password everywhere, if they're using a password on a service for business purposes somewhere else, and you wanted to gain access to that third-party service, it can be extremely difficult. But if they use the same password in your environment, you can perform a targeted password attack against that single user password to then hopefully acquire the password they use on a third-party site. And there are obviously legal issues with that if you were doing that against a third-party site that you didn't actually have legal rights to have access to. So key space makes a huge difference. What I show on the screen here is if you have a key space consisting of 8 lowercase letters, the total key space is 26 A to Z characters to the 6th power. So it's about 308 million characters. Scenario B is if you had a 5-character string made up of lowercase letters, uppercase letters, numeric characters, and 33 special characters. It's 95 to the 5th power, which is about 7 billion. potential passwords, which is larger than the 308 million associated with the longer password. So the gist of it there is that password length and complexity make a difference, but it's in general the length that's going to be more of a challenge when cracking passwords than the password complexity. So you can see here in scenario B, though, it's about 25 times the key space size of scenario A. How many of you have used John the Ripper? It's been around for years, so almost everybody's used that. How about any of the versions of Hashcat? Okay, so about a quarter of you, and what about CryptoHaze Multi-Forcer? Okay, that's good to see. So today we're going to talk about Hashcat and CryptoHaze Multi-Forcer. Hashcat has a number of versions. The regular Hashcat's designed to work on a machine that just has a CPU. Hashcat Lite and Plus are designed to work on machines that have GPUs. So the graphical processing unit is tremendously fast in comparison to a CPU for cracking passwords. The Lite version is only designed to crack a single hash, whereas the Plus version is used to crack a hash file consisting of multiple hashes, usually a large number of hashes. CryptoHaze Multi-Forcer works the same way. It's generally used to do brute force attacks. It can do masking, which I'll talk about a little bit later. And Hashcat has more flexibility because it can do dictionary attacks, combined dictionary and masking attacks. It can do combination attacks that take a list of words from one dictionary and another and combine them. And so it has a lot more different operations that can be performed compared to CryptoHaze Multi-Forcer, but there are some advantages with the Multi-Forcer tool. And all three of these are open source and free to use.
No, not technically.
I'm sorry?
Not technically in Hashcat. It's free to use, but not open source.
Okay, good distinction. So all three are free to use, but two of them are open source and one is not. And if there's anything else I point out that may not be correct, just feel free to jump in. I want to make sure the information I share is correct. So if we were talking about building our own system or leasing it, what are some of the pros and cons? Have any of you ever built a password cracking machine with one or more GPUs? Okay. So can one of you talk about what the components are and what it costs for you to build that? Just roughly.
Okay, so your average cluster, we've got about, let's call it 20 GPU nodes with the new VCL Hashcat OpenMosix type patch they just got out there. So your average component of your basic GPU cluster is the initial node for the machine itself, also used for the Elcom soft type stuff. So you got your standard server board, PCI Express, drop in a pair of Radeon 7970s. Each node for us costs about $2,000 to build. So as we need to go scale out our attacks, we just add on another $2,000, about 5 RU, draw about dual power supply-ish, and they'll take some serious power when they're running. And of course, you need cooling for your server room, the 9 yards to keep it cool. So you budget, you get $2,000 for the actual box, and then operational costs on top of that to keep it cool.
Okay. So one of the things you mentioned is that there's the cooling, so you have to have the infrastructure in place for the cooling electricity. If the hardware fails, you're responsible for monitoring that and making sure that's fixed. What kind of lead time do you have on buying a new piece of equipment and getting that set up?
About a week.
About a week. Okay. So those are some of the constraints when you're working with building your own machine. There's a cost associated with it. Not all of us have $2,000 laying around or 2,000 times the number of nodes we want to build. Some of us have machines that already have a GPU in it that can be utilized, but those machines are typically machines that you may want to use for something else. If it's a laptop, some of the higher-end laptops have GPUs that you can use, but if you're running an attack that may take you more than a day, and you may want to use that machine for something else, there's a risk that it could fail or it's not available for something else you may need it for. So it is economical to build your own machine if you have $2,000 laying around and you have a need to use it on a regular basis. I assume that you do password cracking pretty routinely.
I also have an FPGA farm on top of that, so.
Okay. So that's one option you can go with, or there are other options like utilizing Amazon's EC2 service, which is a utility-based pricing model that I'll talk about in one of the upcoming slides, maybe the next one. Okay, so it's early in the morning. This should hopefully be easy. Does anyone know what this is a picture of?
A river?
clouds?
I've given some hints.
Amazon?
The Amazon River. There you go. So it's the Amazon River. Okay, so it's actually pretty trivial to set up an Amazon EC2 instance. With the Elastic Cloud, to create an account, you may already have an Amazon account. If you do, you can utilize it. Otherwise, you just create one. You give them a credit card number and a phone number, or they send you a code to it, you enter it in, and now you have an account. Doesn't even mean you need to spend money, because they actually have a free service you can utilize. That's not going to be available for utilizing GPU-based nodes, though. So the total time to create an account and then set up an instance, once you know what you're doing, is about 3 minutes, roughly speaking. So the steps to do that are to go to the Amazon EC2 console, which is simply a web page you have to log into. To authenticate your machine, you're probably going to want to create a key pair, so you don't have to use a password. You create a new instance, and then you can log into the machine. And that's about all there is to it. Of course, you have to install some software to be able to crack passwords. Here's what the screens look like for building a system. You can see on the right, I have 2 running instances at this point. But if I was to click the launch instance button, and I apologize, it's probably pretty hard to read. So it takes you to a screen where you get to pick from a number of available types of machines that vary based on the type of hardware in the operating system, and whether they're 32 or 64-bit. There's only one available machine that you would want to utilize for GPU password cracking. And so I would simply select that machine, which is a 64-bit machine. It takes me to another screen, which lets me do things like determine what geographic location I want the machine to reside in if I care about that. And I can also do some other things like put in scripts that will run as soon as the machine's built. So let's say that you want to build a machine, you already have scripts set up to install the hash files you want to work with, the dictionary files that you want to enumerate, and the crypto haze or hashcat software. You can simply paste it in, and when the machine comes up, it will start executing those commands, and the software will be available to you. Okay. So you simply enumerate through a few screens, then you come to another screen that essentially says the machine's being built. Then it takes probably a minute and a half for the machine to actually be built from that point. And if I come to the console, it lists the machines in this particular account that I have already created, and they are either in a running state, a stop state, a terminate state, or I don't actually remember the name of it, the state that it actually says that the machine's being built. And so in this particular case, I have a couple of machines named Exhibit and Vanguard, which are the GPU nodes, and I have some other machines. One is a T1 Micro, which is a free instance that Amazon makes available to you, and another is a CPU-only machine with multiple CPUs in it. Okay, and this screen and the next screen just show more information, such as the IP address and host name of the machine. You can set static IP addresses and associate them with your machines. You don't actually need to do that to do password cracking. It just makes it easier for authentication and management. In terms of the pricing, there's really 3 different models that Amazon has. Reserve pricing, which guarantees you the machine will be available to you for whatever period of time you want the machine to be available. If you want to fire the machine up and run it for an hour, you can. If you want to run it for a month straight, you can do that too. You pay by the fractional hour. So if you use the machine for 5 minutes, you're paying for an hour. So that's something important to keep in mind if you want to control your budget. I'll talk about spot pricing later, but that's actually the most economical method for my password cracking purposes. I'm sorry, what I was talking about before was on-demand pricing. Reserve pricing is the same thing. It allows you to get discounted pricing should you know for a fact that you want to utilize the instance for multiple months. So you pay an upfront charge and a lower hourly charge. And so if you do the math and determine that it's going to be more economical for you, you can do that. For me, doing penetration testing or internal work for my organization, I'm not running a password cracking box for days at a time, so I don't opt to use that methodology. In terms of the purpose and configuration, that's where you pick the operating system, and you pick whether it's Linux. There's many versions of operating systems you can use. Essentially, it breaks down to Windows and Linux. Windows tends to be a little bit more expensive than Linux in terms of the hourly price. Geographic regions have a little bit of difference in terms of pricing. For password cracking, you could pick instances that are in locations in the United States data centers. There are also European, Asian Pacific, and I believe some other locations you can pick from as well. Yes?
I actually, just about a year ago, played with like FTK's distributed password cracker, and I found that the agent runs under Wine under Linux, so I was able to keep my costs down by still choosing Linux, even though the agent, the stuff I was using was Windows-based and I did it under Wine.
That's good to know. I haven't actually done that, but that's a really good point. So essentially what you pay for on top of that is your data transfer. You pay a pretty nominal rate if you want to have a static IP address. And if you want more detailed metrics than they make available, you can pay for that as well. Those costs are really trivial when you talk about password cracking, because we're not talking about moving terabytes worth of data. I'm just curious, for your organizations, do any of you have databases in your organizations with millions of passwords? Okay. That would make sense given the password attacks that you're performing. But most of us are working with smaller databases than that. And so it's not going to require a lot of storage, but even with 1 million passwords in a hash file, it's a trivial amount of storage. And the difference in running an attack against 1 million passwords versus 10,000 passwords, it's not a linear relationship, so it doesn't really make a tremendous amount of difference. This screen is just an example of some of the pricing for some of the CPU instances. So you can see on a Linux machine for a small instance, 8 cents per hour, up to an extra large machine being 64 cents per hour. I don't actually know the differences specifically between those two. They're provided on the Amazon website, but it's probably more CPUs in the extra large machine, a lot more RAM, and potentially more storage.
Are these GPU instances?
No, those are all just CPU instances. So I'll be getting to the GPU. It costs $2.10 right now per hour to utilize for the reserve pricing.
And is there, is there a minimum that you have to use it? I mean, that says 8 cents, or the one for GPUs is different, but you can fire it up for an hour and use it for an hour. There's no minimum.
There's no minimum, and you can basically stop it whenever you want. So if you want to run it for an hour, stop it. You're not, with some caveats, you're not really paying for anything while it's stopped. So if you want to set up a machine, run it for an hour, turn it off, and run it a month later, it can just sit there idle, and then you can re-enable it when you next want to use it. Sure. So I want to mention the T1 microservice just because if you haven't used Amazon EC2, I strongly encourage you to try it for 12 months. And I have no incentive to tell you this, but for 12 months you can run a Windows machine and you can run a Linux machine. They're not very beefy, but if you just want to play around with them, they're free. And you get 750 hours of use on each of them, I think 30 gigabytes of storage and 15 gigs of transmission per month for free. And in terms of the instances that I built for testing, I actually did more than this, but these are the ones that we're using for comparison. And I may say we sometimes and sometimes say I. I had a co-presenter that helped me with the research, and we presented this elsewhere a couple of weeks ago. He wasn't able to make it with me today. His name is Randy Todd from UTSA. So I'm giving the presentation by myself. The first machine is called M1.large. You can see it has a pretty fair amount of RAM. In terms of the processors capabilities, Amazon describes it in terms of EC2 compute units. Does anyone know what an EC2 compute unit is? So that's not really going to mean a lot to a lot of people. It's essentially the computing power in I think about a 1 gigahertz, I think it was Opteron computer from 2007. So they measure everything in terms of that as a baseline. So that gives you an idea of how powerful that particular machine is. And the cluster GPU Amazon unit runs a Amazon version of, it's either Red Hat or CentOS, and it has a lot more RAM, and it's quite a bit more powerful in terms of the CPU, and it runs 2 NVIDIA Tesla GPUs, which are actually fairly expensive GPUs, but are not really the best GPUs to use for password cracking. The service is really designed for doing things like analyzing data for biochemistry or oil field analysis or stock markets or things like that, or visualization. So these are GPUs that are fairly expensive. I want to say roughly in the $1,000 range. Does that sound right to anyone who's priced them out?
I think when they came out, weren't they like 10? Yeah, 10 grand a card, something like that.
Okay, they're that much? Okay.
There's still a couple grand, yeah.
Yeah.
Okay, so they're quite a bit magnitudes more expensive than a GPU card that you would have put in one of your boxes, which I'm guessing is probably
$500 a piece.
$500 a piece. So if Amazon does make a service available with those types of cards, they'll actually be able to crack passwords at a faster rate and at a lower cost, but it is still fairly economical. But since inception, those are the only cards they've had available. The third machine we utilized for baseline testing was a fairly old laptop with these particular specs. Yeah, got some chuckles. And so that machine's called Zelda. It really had no cost to us. I mean, there's a nominal electrical cost, but it's a laptop that we could plug in whenever we want. The Yoda machine, which was the Ubuntu server running the CPUs, cost us 32 cents per hour, and the GPU machine costs $2.10 per hour, so it's a little less than 7 times as much. In terms of testing, we actually tested against a number of password databases. This was a good one to use for demonstration purposes. So eHarmony made about 1.5 million passwords available. Well, actually, they were compromised. It's kind of interesting. Can any of you read what it says above the eHarmony logo? #1 most trusted online dating site. I guess not #1 most trusted in terms of protecting passwords. So this is just what the hash file looks like. It didn't have any usernames associated with it, so the hashes were unique. So we can't actually tell from our analysis whether certain passwords were used by more users than others, like you could with something like the RockU compromise, because with RockU they actually had, I believe it was the email addresses or usernames. Using Hashcat Plus, we performed the following types of attacks. A dictionary attack just enumerates a dictionary file. Now, a dictionary file doesn't have to be a dictionary like the Webster's Dictionary. A dictionary is just something that has a series of strings in it. So it could be the Webster's Dictionary, a list of first names, a list of places, song titles. It could be anything that you can come across that consists of a string. A combination attack takes a word or a string from one file and combines it or concatenates it with a string from another file. So it's essentially merging a couple of dictionary files. Rules allow you to do things like transformations, change E's to 3's, S's to $signs, shift letters, duplicate letters, and things like that. And masking is a form of brute forcing that allows you a lot more granularity, which reduces the time that it takes to perform an attack. So a brute force attack is just simply trying every possible combination of passwords that are in a particular key space. Dictionaries didn't actually prove to be very effective, so I'm not actually going to show you the statistics with that. They were somewhat effective, but it was definitely not the most effective option available, and I utilized a lot of different dictionaries. All of them were English words, but I used first names, last names, places, lots of different things, and they just were not very effective by themselves. Another way to do it is to use leaked password files. So I did do that, use things like the RockU password database, which was about, I think, 15 or 17 million unique passwords, and use that as a dictionary file. Using a bigger dictionary file is not necessarily going to be more effective than using a smaller one. It's sort of a case of garbage in, garbage out. If you have tens of millions of strings that are not going to actually ever be used as a password, then you're just using a lot of processor time for not any gain. So with a combination attack, essentially what I did was took one dictionary, combined it with another. I had a number of English dictionaries that I joined together just by sorting them and removing duplicates using the Linux unique command. And that had about 386,000 records, which when you square that is about 149 trillion combinations. Running that attack on the GPU machine took 321 seconds, so that was about 464 billion passwords per second. But that wasn't really just 464 billion passwords per second. Does anyone know why? Want to take a guess? So what that was doing was enumerating through 464 billion of the combined passwords per second against the 1 million passwords that were being tested. So it was actually doing 464,000 trillion attempts per second. And what I did was, just for simplicity for math, took the first 1 million records from the eHarmony database. The results would be very similar if I used the entire 1.5 million password data set. 79% of these passwords were rejected because they were too long, and that's because Hashcat has a 15-character maximum. So if it was combining an 8-character string with an 8-character string, it exceeded that 15-character limit, and it basically discarded it. But using this methodology, 123,000 passwords of the 1 million were recovered. So that's not too bad, 12% for 5 minutes of GPU time. Okay, I had a second dictionary that I think my math might be wrong here. Okay, I had two different sets of dictionaries. One consisted of passwords from other leaks, and one consisted of English dictionary words, places, names, and those kinds of things. This is a second one that involved passwords that were leaked from other sources. The number of records here is incorrect, unfortunately. Let's see, maybe that was just a duplicate slide. So in terms of the syntax, here's the syntax you would use with Hashcat Plus. The syntax for Hashcat Lite and the regular version of Hashcat are slightly different. Essentially, telling it an attack mode 1 is a combination attack. You can also tell it what format the hashes are. By default, it assumes that they're MD5, so I haven't actually applied that parameter. Here's my hash list file, the two dictionary files I want to combine. Then I want to store the output of the cracked passwords in this file, and there was some data associated with the run that I want to store, such as the number of passwords it enumerated, how long the attack took, and that type of thing, and I stored those in a separate file.
So, by running Hashcat on the Amazon GPU machine, did it just identify that those GPU resources were available and use them, or did you have to do some special configuration?
I didn't have to do any special configuration. I did make some upgrades to the drivers, but that wasn't actually necessary to run the tool. So no, it automatically does that. It does supply parameters so you can tell which GPUs you want to utilize, but by default, it's able to look for them and utilize the GPUs that are available. So using the second variant of the same attack, it took a little bit less time, and it resulted in matching 11% of the records, but it took half the time of the previous test. So one thing I want to point out is, depending on the test that you're performing, it may not use all of the GPU. And so for these particular tests, it was not using anywhere near 100% of the GPU. So sometimes you're not going to get all the gain that you would expect. So by performing these types of attacks a lot, it's easier to determine how long a particular attack might take. And I utilize that to do some more automated testing where I take specific rules and estimate how long they're going to take, and then hand them off to various GPU nodes. When I talk about distributed attacks later, I'll get into a little bit more detail. So, whoop, that is not good. I jumped to the end. Okay, so I ran 4 different combinations, and combined they cracked 17% of the passwords and took 17 minutes. So if I was to run them on the GPU node for an hour, I still had excess time that I could utilize to run other attacks. So next I ran some rule attacks, and they look like this. These are some of the rules that are available. These aren't all of them. And what this chart on the Hashcat site shows you is with these different rules that you can supply in a rule file, how you can modify the types of passwords that it's going to try to guess. So you can see it does things like convert these strings to lowercase or uppercase, capitalize specific letters, reverse the string, and that type of thing. So one of the rule sets that comes with Hashcat is a list of 64 rules that I ran. And I want to point out that my goal was not to crack 100% of the passwords, because I don't really care about cracking 100% of the passwords. In a real world scenario, what I care about is demonstrating to someone that I can crack a large percentage of the passwords pretty quickly, to do things like demonstrate that the password policy is insufficient, or users are not creating strong enough passwords based on the password policy that's in place. So, you know, an 8-character minimum with a number required and a capital letter required. A lot of users are going to create a capital letter for the first character, and then use lowercase for the rest and put a number at the end, and it's often going to be the number 1. So had I want to run this longer, I could have gotten closer to 90% in a few hours against this data set. But with this particular rule set, in 9 minutes, I was able to crack 49% of the passwords. Yes?
This is on the instance that costs you $2 an hour?
$2 an hour. And I'll talk later about what the same tests, how long they would have taken and how much they would have cost on other machines. Now, this 49% is not necessarily different than the 17% from the previous test. There was a little bit of overlap, so we can't assume that it could have been run for 17 minutes to get 17%, another 9 minutes to get 49 additional percent. There's a little bit of overlap between the two cracked password lists that were generated. Masking is probably my favorite password attacking methodology that Hashcat utilizes, and CryptoHaze Multi-Forcer also utilizes it. It's like brute forcing, except you can specify with more granularity how you want the attack to be performed. So one of the things that I learned from the eHarmony data set was eHarmony did something pretty stupid. Does anyone know what eHarmony did that was pretty stupid in terms of how they stored their passwords? Besides the fact they were unsalted MD5s. They performed a manipulation on them before they stored them.
Didn't they convert everything to uppercase?
So they converted everything to uppercase. So once I discovered that, which was pretty easy to discover by performing my first dictionary attack because it resulted in a very low success rate, I ended up converting all my dictionaries to uppercase because there were no lowercase passphrases or passwords in the eHarmony data set. So that actually made it a whole lot more simplistic because it didn't make it so I had to attack half the same key space. It's actually a factor of 2, because instead of looking at 52 characters to the nth power for the number of strings, it's 26 to the nth power for the number of strings. So if you're looking at a 8-character key space, just consisting of uppercase letters versus upper and lower, it's 1/128th, I believe, the size. Does that sound right? 2 to the 8th power? 256? Okay. So it's 1/256 of the key space, which means, well, I show that right on the slide. So it makes it a lot easier, so it takes a very small fraction of the time to do that. So using the masking, you can do things like, say, only test strings that have a first character consisting of the letter A, followed by 4 characters that are numeric, followed by 2 characters that are special characters. And that makes it a whole lot easier. So this is one of the strings that I utilized. The -1 $U means that I want to create a parameter called -1 that consists of uppercase letters and a parameter of -2 that consists of decimals or numeric strings. And I want to create a pattern. The second question mark shouldn't be there. That should follow the first one. But what this should be is I want to look at a string that consists of 1, 2, 3, 4, 5 uppercase letters followed by 1 number. So by doing this, I ended up creating, for this particular demonstration, 26 masking attacks. They took a combined 50 minutes to run on the GPU node. It's probably a little difficult to see, but the test took between 8 seconds and 3 minutes in general to run until I got to the last test. I have columns here that show the number of strings or the key space, the amount of time in seconds it took to run the attack, which I automated just by running bash scripts, the rate, which is the number of strings that were tested divided by the number of seconds, and the number of strings that were cracked, and a separate rate for that, which was the number of strings cracked divided by the number of seconds the attack was performed. And you can see at the end, the total number of passwords cracked was 404,000, so about 40% of the database. And it took
50 minutes.
50 minutes, and that's largely because the last test I ran took close to 30 minutes. It took 1,705 seconds because it was looking at a substantially larger key space. That test was looking at all strings that began with the letter T, followed by 8 more characters that were either uppercase letters or numeric strings. Does anyone know why I chose the letter T? So the letter T is the most frequent first letter in English words. It makes up like 17% or so of the English words by first letter. If you go down to Z and Q, they're a fraction of 1%. So if you had limiting processing time, or you wanted to prioritize, you probably want to start with letters like T and A, which are the most frequent, and wait to do Z, Q, and X. Or you may never even want to test those. So it really depends on whether you're trying to crack a specific individual's password, or you're trying to crack a large percentage of passwords to demonstrate the weakness of the password set. So those are the kinds of things that I do to prioritize. And you can see some of these tests were more successful than others. An interesting deduction from this was that there were very few strings that actually had special characters. So I learned not to even bother including special characters in the tests that I performed. And so when I do a test like this, I actually have some scripts set up that analyze the output of each individual test and automatically determine whether subsequent tests should be performed. So if there's no lowercase letters, it excludes subsequent tests that involve lowercase letters. The same thing with special characters. Or if it sees anything that's unusual about the pattern of passwords that are cracked, it manipulates the rules that are created and run later on, because none of us have unlimited processing time. So even if it costs $2 per hour, it doesn't make sense to run it for 20 hours if you can get the gain that you need by running it for 2 hours. So this took about a little less than an hour to run. Do any of you want to guess how long it would have taken on the 2 other machines, the really slow laptop or the Amazon machine that was just running a couple of CPUs?
4 years.
So those are pretty good guesses. So these are the rates that these machines were able to crack passwords at. There are some caveats. Exhibit was not able to consistently crack at 1.6 billion passwords per second. If you look at the previous screen, it averaged 1.2 billion password attempts per second. And that's because some of these attacks that were earlier on did not actually utilize a large percentage of the GPU. Yes?
Do you know how many GPU cores you had available to you?
It's 2 if I remember right.
Yeah, 16?
Yeah, it's 2 of the Teslas, isn't it? On those?
It's 2 of the NVIDIA Teslas.
Yeah.
Do you know what model Tesla?
C2050, I believe. So if we look at, on a comparison factor, Exhibit was 114,000 times as fast as the laptop and 258 times as fast as the CPU machine. So even though this Exhibit cost about 7 times as much as the CPU machine, it was 258 times more effective. So if you take 258 and divide by 7, that tells you how much more cost effective it was. So for the hour processing time on Exhibit that cost $2.10, it would cost $82 on the CPU machine. So the only time I would use a CPU machine is if my budget was less than $2.10. Does anyone have a different viewpoint on that?
So, it's gonna, if you're doing this for the first time, it's gonna take you some time to set it up, figure out the scripts. I assume you could do that on the cheaper machine and then fire up and move it over to the more expensive machine.
Yes and no. The software won't actually run on a machine that doesn't have GPUs, but you could run on a local machine with GPUs, or I can make the scripts available to you and you could just copy and paste them, and there wouldn't be much of a learning curve that way. And I'm definitely glad to do that. So if any of you want my scripts, I'll be glad to share them. So you can see it's almost 4,000% more cost effective to use a GPU machine.
Are you going to touch on the spot instances and the savings that you can get?
Yeah, I'll get into that momentarily. So I'm going to fly through some of this just so I can get through the entire presentation, but what I look at is what are my constraints. If it's a deadline and my boss comes to me and says, I need this by 2 days from now because I need to go to the board of directors and talk about the password policy, I don't have time to buy some hardware and wait a week for it to come in and set it up and do all that. I'm going to fire up a number of nodes running GPUs. Is probably what I'm going to do. But my constraints might be cost, or I may have machines laying around that I'm willing to do it myself. So it really depends on what my needs are. So there's not a one-size-fits-all here. So the spot instances, here's the screen to set that up. Essentially, it's a bidding process. Right now, it costs under 35 cents for a spot instance of the GPU node that would normally cost $2.10 per hour. So what I would do is go in and say, I'm willing to pay up to this amount per hour for a spot instance. And so I might say I'm willing to spend 40 cents per hour. It's only going to charge me what the actual rate is. So if the rate's less than 40 cents per hour and it's 34.6 cents, that's what I'm going to end up paying. And I decide how many of the spot instances I want. So I might say I want 10, and I'm willing to spend 40 cents per hour. If I spent 40 cents per hour, I'm going to spend $4 per hour total for 10 total machines. So I walk through these screens, and I can tell it